Good morning and welcome to another Guideline Geo webinar. Today on the topic of 3D resistivity surveys and specifically doing those with the ABEM Terrameter LS2. We're a few minutes past the hour, so I think we'll make a start. We will be recording this session, so if anyone misses it, they can catch up later. A little bit of housekeeping just to start with. If you have any questions as we go through, please put them into the chat box in the Zoom window. And then when I get to the end, I'll review the questions and answer any that I can at that point. And if there's any that I can't answer immediately, then rest assured that I will contact you afterwards with an answer. Okay. So the agenda for this session is I'll give you a brief introduction to myself and the company in case you haven't been to one of our webinars before. If you have, be a good chance to get a cup of tea. Then we'll move on to a brief introduction onto what ERT is. This is really a beginner's session. It's just an introduction to 3D resistivity. So we'll start very basic and make sure we're all using the same terminology and understand the fundamentals of what we're trying to achieve. Then we'll look at the practicality of trying to collect 3D data, what we have to do in the field in order to be able to get that data set. We'll also look at the difference between true 3D survey and what is known as 2.5D survey and the advantages that actually collecting data in that fashion bring. Then we're going to look at the spread and protocols, i.e. How we set the instrument up in order to collect this data. We'll also look at the generic processing steps that we would go through to go from raw instrument data to a model that we can visualize of resistivity values. And then we'll actually do a slightly more practical part. I'll connect to an instrument that I've got here, and I'll just show you the process of how we would set the instrument up to do a measurement, start it running, and then we'll kind of go through the steps that I've talked about with the data processing in some software and have a look at some data. So a lot to fit in the next, let's say about 50 minutes. So strap yourselves in. So my name's Jimmy Adcock. I am the product manager for the ABEM line at Guideline Geo. I started being involved in geophysics in the late 90s when I went to university, and then came straight out of there and went into employment as a surveyor. I joined Guideline Geo in the summer of 2015 as an applications engineer, doing technical support, sales support, customer training, demos, that kind of thing. And then moved on to be the product manager around 2020, 2021. Guideline Geo, if you don't know that much about us, we are a manufacturer of geophysical solutions, both hardware and software. We were established in 1923, so this is a big year for us. It's our centenary. And we have two brands. We have the ABEM and Mahler brands. Everything is made in Sweden. And we have a pretty large footprint across the world. We've got sort of representation in about 80 countries, and I think a total of around 90 employees spread out around the world. So as I say, this is our spread. We cover most of the time zones pretty well. These are a combination of both technical offices and sales offices. I'm based in Manchester in the UK. Headquarters of the company are in Stockholm. Our research and development office is in Umeå, and then a little bit further north, about 100 kilometers short of the Arctic Circle, we have our factory up in Malå, where we make everything. So we've got two brands, Malå, which is the ground penetrating radar systems, and ABEM, which is resistivity, seismics, and time domain electromagnetic systems. And we have a huge number of partners and customers that we've been involved with over the years, both in the commercial sector and also the academic world. Okay, enough background. Let's get on to what we're here for. And that's to talk about resistivity survey, specifically 3D survey. So what is ERT and how do we go about collecting it? Well, if we start with a more common scenario, that is collecting 2D data, well, then we have a line of electrodes inserted into the ground. They are attached to a resistivity meter, and within that meter we have a switch box that is selecting different electrodes to inject current and selecting other electrodes to measure voltage from. We then run through a sort of script of measurements in order to build up a raw data set, what we call a pseudo section of raw values, apparent resistivities, i.e. the resistivity as measured from the surface. And then we will put those through a processing package, an inversion software package, in order to go from that raw apparent resistivity to what we hope are true resistivity values. That will then allow us to make an interpretation. We can make an interpretation in really one of two ways. One is an sort of going off absolute resistivity values. So we might say, well, we're looking for a particular type of geology and we expect it to have a resistivity range of X to Y. And so we are looking for values within that range, and we would apply the interpretation to those values. What is probably more common is that we are looking for relative change in resistivity as something to identify a material or structure within the ground. So things like landfill deposits, pollutants, fractured rock, which holds more water than solid bedrock, materials like clay, the presence of salt or salt water, and just having greater water content in the ground will all serve to reduce, in most cases, the resistivity from its natural value from the host material. And conversely, if there is a reduction in water content, if we have free draining materials like sand and gravel, so there's less water to conduct the currents, if we have good solid bedrock with no fractures to hold water within it, building foundations, voids, air gaps, the presence of oil or even frozen ground, all of these things impede the flow of current and cause the resistivity to increase. So there is a very, very wide range of applications for resistivity survey, and it's why it is one of the more popular geophysical methods. So that's 2D. What happens when we want to move from that single slice through the ground, looking from the surface down, to looking at a larger area, looking at a volume of data? Well, in that instance, instead of just having a single line of electrodes laid out on the ground, we would want to ideally lay out a grid of electrodes. And then we go through the same process. We inject the current at one location and then measure the voltage at one or more other locations whilst that current is flowing. And we move through that grid in the most simple way, just along the rows of electrodes and then across the rows in the opposite direction at 90 degrees, as being shown here. But we could also do diagonal measurements, and we could do novel arrangements of electrodes that might bring a particular benefit in terms of their sensitivity to particular structures. Once we've collected all of that, then again, we have a raw data set of apparent resistivities, resistivity as measured from the surface, because imagine if I'm trying to measure down here at depth, the current has had to flow through these upper layers to get there. So all of this volume, all of this subsurface material is contributing to what I measure. So my raw data set of apparent resistivity values are then taken forward into the inversion software, and we will run the inversion as we did in 2D to produce a model of, again, hopefully true resistivity values, but now with a volume that we can interrogate by slicing horizontally. So we can look at resistivity variation in plan, which can be very useful for determining the extent of features, or we can slice through it vertically in any orientation, again, so that we can kind of recreate that 2D view, but in the direction of our choice. So laying out a grid of electrodes is not as simple as just putting a single line of metal stakes in the ground and then hooking them up to your cable. There are certain practicalities that come along with attempting to make these measurements. So if we lay a grid of electrodes out, there are a number of ways in which we can actually connect to those, hook them back up to our Terrameter LS2. A very simple way would be to just have a single multi-takeout cable with electrodes attached to it on each row. So each row of electrodes here is a single cable, and that single cable goes back to one of the inputs on the instrument. So line 1, line 2, and then we've got expansion units to allow us to have more electrodes, line 3, line 4, line 5, line 6. And all of those are connected together and operate as a single instrument. And that then allows us to have our grid laid out. Another alternative would be to use our regular multi-core cables, our regular takeout cables, but this time we might want to manipulate the dimensions of the grid. So rather than having the width a complete cable length, we might want it to be less than that, in which case we can zigzag the cables through that grid of electrodes. So on the instrument itself, we can effectively tell it exactly how we've laid the cable out. We just assign an X, Y, and Z, if necessary, position to all of the electrodes, and just tell them which takeout on which cable that particular electrode would be attached to. So although it might look complex on the ground, as far as the instrument is concerned, it's quite simple. This electrode is attached to takeout number 1, and it is at these coordinates, X, Y, and Z. Another alternative, which might be useful if you've got a very complex 3D layout, or working over maybe some unusual terrain, or if you're thinking about the flanks of a dam or something like this, where perhaps trying to weave a multi-takeout cable around might be difficult, then we can actually use what's called a breakout box. And that allows us to split the multi-pin connector that's on the end panel of the instrument into individual wires. So we just have plug in at one end, clip on the other end, take that straight out to the electrode. Also very useful if, for example, your 3D measurements aren't necessarily in the real world, but in fact in a laboratory. Perhaps you're modeling the impact of water seepage through a dam. You've built a scale model in your lab, and it wouldn't be feasible to have a regular multi-core cable zigzagged through your laboratory to connect to those. So you could use a breakout box, much lighter weight cables running to the pins on that model, and then recreate the survey in that way. So those are the methods that we would use for laying out the 3D grid. There are other issues that come along with a desire to undertake what we call true 3D, so where we have this grid and we're measuring in all directions through it. And one of the problems that we've got after we've got around the practical layout issue is just the sheer number of data points that we might need to collect. When we have a 2D profile, once we've kind of designed our survey parameters, it's usually a fairly manageable number of data points. It might be 1,000 or 1,500 data points that we want to collect over a 2D profile, fewer if it's something simple like a Venner or a Schlumberger. And that's because we know that there are certain constraints on resolution, so there isn't a need to actually take every possible combination of electrodes. But when you move into the 3D space, then we have far higher number of possible electrode combinations, because we're not constrained to choosing electrodes in just a single straight line. We now have multiple lines, and we can collect along them and across them and diagonally, and as I say, even novel approaches where the electrode arrangement might be in a square or something similar. So that starts to ramp up the number of data points into multiple thousands of data points. And so therefore, your data collection time is going to start stretching. Not only that, the more data points you have, the more times you'll need to inject current. And so therefore, you need to think about the powering solution. You know, how am I going to provide enough power to the instrument to be able to complete this measurement, especially if I'm somewhere remote where perhaps, you know, it's not feasible to just plug in to a wall, or, you know, I might not be able to take a huge number of external batteries or a big heavy generator out with me. So we want to think about ways that we can make it more efficient. And one of those is to be sensible about the choices we make in terms of which electrode arrays we use, the configuration of electrodes that we use. So when we say we're going to inject current in through 2 electrodes, measure the voltage in another 2, there are some constraints that come with our choice of arrangement. So some arrangements of electrodes are what we call single channel measurements. And that means that when we're injecting current, we can only measure voltage in one location. It's kind of predetermined by the choice of electrode configuration that we've made. Whereas other electrode configurations are what we call multi-channel. And that means that whilst you're injecting current in one location, you can be measuring the voltage in multiple other positions at the same time. And so therefore, you can move through that list of positions much more quickly in fewer current injections. So as a real world example of the configurations that fall into these 2 categories, Venner and Schlumberger, they are both single channel arrays. Quite obviously with the Venner, so for a Venner configuration, we have an equal spacing between all 4 electrodes that are in use. That's what defines the Venner configuration, the Venner layout. So that means that as soon as I have defined which 2 electrodes are going to be injecting the current, the 2 positions where I'll be measuring the voltage are predetermined because the spacing between all of the electrodes has to be the same. And so therefore, I can't measure voltage in any other position if I want a true Venner measurement. So for that configuration, when current is being injected between A and B, I have to measure between M and N, which gives me a focus position, the point at which we assume the apparent resistivity has come from. We have that one position. Then move the current injectors, that defines where the next voltage measurement will be taken from, and there's my second data point. So if I have, let's say, 1200 data points to collect in my 3D layout, and I'm using Venner, then I'll have to inject current 1200 times in order to complete that list, and 1200 repetitions of the measurement cycle. Same is true for Schlumberger. The position of the current injectors is defining how deep our focus position is, and where it sits laterally. And then for a Schlumberger, our voltage pair, like the Venner, are bang in the middle, but they don't need to be equally spaced. They can be closer together or they can be further apart. It just influences the signal strength, but they still need to be at the center. And so therefore, once A and B are defined, our focus position is kind of fixed, and the point where we would need to take the voltage reading from is also fairly fixed. So what we really want to do is use something that has more flexibility. And so examples of these are dipole-dipole, the multiple gradient, the pole-dipole, and the pole-pole measurements, electrode configurations. So in the example here, we've got a dipole-dipole, where the current is being injected in this example on these 2 electrodes, and then the voltage is being collected on this pair, this pair, this pair, and this pair simultaneously. And so that is giving me, whilst the current is flowing in just one position, a number of data points. So I'm crossing off a number of positions on my list of measurements in one current injection. So again, that's speeding up the process and reducing the power budget required for a particular survey. The number of measurements that we can make whilst the current is flowing is really determined by how many channels we have available on the instrument. How many measurement circuits does the instrument have? Because then I can utilize those to select different electrodes whilst the current is flowing. There are some other slight caveats to how many points you can collect at any one time. One is that you physically have to have the space to be able to do it. So if you imagine in this example, if A and B had a wider spacing, so we were putting current in on the first electrode and taking it out somewhere up here, there are fewer positions left on the cable where I would be able to take a voltage reading from. So there are physical limitations, and also perhaps within the design of the switching unit inside the instrument, there may be times where it's not possible to use all channels at once. But the primary thing to look at is how many measurement channels does the instrument have, because that will definitely be my maximum capacity for measuring voltage whilst the current flows. If we're doing these true 3D surveys where we have a grid of electrodes, then another limitation that is thrown at us is the depth that we can achieve. So for resistivity surveys, there is a rule of thumb that we can use to determine what the maximum depth we might reach is with our measurements. And that is, we take the spread extents, like how far apart are the furthest electrodes, and we divide that by 5. It's actually somewhere between 5 and 6, but we'll be generous and we'll divide it by 5. So it's approximately 20% of the spread extent. So if you have a 2D survey where all of your electrodes, however many they might be, 64, 128, 1,000 and whatever, they're all in one big long straight line. And so 20% of that very long line is hopefully something nice and deep. As soon as we start laying electrodes out into a grid, we very quickly contract the extent of our survey area. And so therefore, if we're contracting the extents, that 20% value is going to get smaller and smaller, and our maximum depth will become shallower and shallower. So in a really simple example, if you imagine having a 64 electrode setup, and you just put that into a square grid of 8 electrodes by 8 electrodes and 2 meters between each of them, that would give us a total of 2, 4, 6, 8, 10, 12, 14 meters east-west and 14 meters north-south. 20% of 14 is 2.8. So we're limited there to around 3 meters. So obviously this is the kind of survey you would be doing for some kind of engineering, maybe an environmental study, looking at landfill, archaeological projects. They might be using these 3D resistivity methods. But you really need to consider how deep you're going to be able to achieve. So how big a spread do I require? And that's a case of balancing your electrode spacing, which is going to define your resolution, with the number of electrodes that you have available. So if you were an archaeologist, you're in pretty good territory, because although you would need good high resolution to be able to map these smaller structures, small walls, ditches, pits, things like that, even though you need a small spacing, generally archaeological features are relatively close to the surface. So the fact that your depth is limited isn't a problem. If you're talking about engineering or environmental surveys, well, then you might be in a bit of a problematic state, because then you might need a close electrode spacing for good resolution, but you might need to go much deeper. You might need 5 or 10 meters, maybe more. If you then move into something like, water prospection in a complex geological environment, well, then you need to go much deeper, but at the same time, you might not need quite such good resolution. So you can afford yourself a larger electrode spacing to increase the spread extent. If the sums don't work out and the resolution that you require with the number of electrodes you have available doesn't allow you to reach the depth that you need, well, then you need to look at expanding the capability of the instrument, adding more electrodes to the system. That's really the best way in order to be able to increase that maximum depth when doing these true 3D surveys. We can stretch it slightly, however, from this 20% value by using either the pole-dipole or the pole-pole survey methods. So with these survey methods, we utilize either 1 or 2 remote electrodes. So if it's a pole-dipole, we have one of the current injectors positioned a far distance from the instrument. And if we use a pole-pole survey, we have one current electrode and one voltage electrode positioned a long distance away from the instrument. When I say a long distance, the theory states they should be an infinite distance away from the instrument. Practicalities, again, not going to happen. But if you look in the textbooks, generally the consensus is that if your electrode is positioned 15 to 20 times further away from the instrument than the maximum spacing between your electrodes, between your electrode measurements. So for a pole dipole, it would be 20 times the distance between the current injector that sits within your grid of electrodes and the voltage pair. And if it's a pole-pole, then you have one current and one potential within the grid. Whatever the maximum distance between those will be, times that by 20, and that's where your electrode should be. If you bring those electrodes closer, then you should theoretically inform your inversion software that that is what you've done, that they are no longer at infinity, or at least the practical version of infinity. And what happens is that as those come closer, those remote electrodes, back towards your grid, that depth of investigation starts to come up. So if you position that remote electrode far closer than the theoretical ideal, but don't tell the inversion software that you're not using that ideal, then what will happen is the inversion software will assume that the layout is correct. It will therefore assume what the maximum depth will be, and you would end up with a model that does not represent what is really beneath the grid, mainly because it is assuming that the current is flowing deeper, that the sensitivity of the system is deeper than the reality. So these can be problematic because these distances can become very large very quickly. On the plus side, you only need a very small, lightweight, single core cable out to that single electrode. So it is possible to run these things kilometers away. And really, it's just being able to work out what is practical in the area that you're working. Can I use this method in order to be able to punch deeper beneath my grid of electrodes? If it's not possible to either expand the number of electrodes available to the system, or it's not feasible to use a pole-pole, pole-dipole type arrangement where you can push the depth to either about 30% of the pole-dipole and somewhere between 50 and 80% of your spread extent for pole-pole. If you can't do that, that's not going to happen. Then another option is to use what we call 2.5D survey. So with 2.5D, we take a series of regular 2D measurements. We take all of our electrodes, lay them out in a single line, collect the resistivity, apparent resistivity values, as we would in a normal 2D survey. We then shift the line across and we measure again. We shift the line across and we measure again. We shift the line across and measure again. We can then take the raw data from each of those profiles, combine them whilst they're still in their raw format into a single 3D block of data, 3D block of apparent resistivity values. We then present that to the 3D inversion software in order to run the inversion and produce us a model of, hopefully, as I say, true resistivity. And then once we're there, well, then everything from that stage onwards runs the same as a regular true 3D survey. We can use the same inversion parameters. We can then slice the block as we see fit, do thresholding where we remove low resistivity or high resistivity values just to leave us with the volume we're interested in. It's a very, very common method of creating a 3D data set because when we do a 2.5D survey, the data collection is very straightforward. It's what we're used to doing if we've done 2D survey. We use our standard spreads and protocols. So our spread is what tells the instrument where the electrodes are, protocol is the measuring sequence. So all the normal survey methods that we would use for 2D, we're just doing that. And the difference comes when we do the processing. The initial stages of the processing are very similar. So we would just do some basic filtering on the values, and then we combine it into that block and then give it to the 3D software. And as I say, at that point, then we would run it as if it was a true 3D data set. Normally, the the easiest way to undertake these surveys is to run parallel lines. You can also put perpendicular ones in, but a perpendicular mesh of profiles is easier to handle than a random path, but that is also feasible. By doing that 3D inversion, rather than say inversion on each of the 2D profiles and kind of interpolating between, that 3D inversion will account for what's happening between the profiles perhaps a little bit better than just inverting as a 2D dataset and then trying to kind of fill the gaps afterwards. And that's because when we do a 2D measurement, it's all in one plane, and we assume that there is no variation to the distribution of resistivity values that we see to the left or to the right of that line of electrodes. We assume that that pattern of resistivity is true to the horizon. So if we run an inversion on that 2D profile, then try and combine it with other 2D profiles, there is a fundamental flaw in that. There's still a flaw in doing the 2.5D method in so much as we're having to make pretty broad assumptions about the data we're collecting, the raw data we're collecting. You know, that 2D measurement doesn't take into account the fact that there could be high or low resistivity bodies just offline that are still impacting the measured value. But it's better than just relying on the 2D values themselves, the 2D profiles. Theoretically, when you do 2.5D survey, the rule of thumb is that the spacing between the profiles that you are collecting shouldn't be more than 2 to 3 times the spacing between the electrodes. I see people sort of playing pretty loose with that and sort of going 5, 10 times. But in reality, what happens is that the further you space those lines out, the further from reality your inversion is going to be, because it's impossible to determine really what is happening between those lines if they are too broadly spaced. So running a 3D inversion on a very broadly spaced set of lines when your electrode spacing is very close doesn't really make sense. It's kind of a waste of the method. So that's kind of all of the theory part and the practicalities in terms of how the measurement works. So I thought I'd just quickly touch upon spreads and protocols. So this is now becoming more instrument specific because when people come to do 3D surveys, it tends to be a little bit more custom than it would be with a 2D profile. If you're doing 2D survey, most people are quite happy to just take the preloaded measurement scripts on the instruments and run them as, you know, a good robust method of collecting the data. But when we move into the 3D realm, well, what often happens is people say, well, I don't actually want a square layout because maybe I want to stretch it into a rectangle, so I get a bit more depth in one direction, and then I just get a slightly shallower sample across in the other direction. It might be that your 3D survey is on a very specific target. It might be around a structure. It might be on the face of a dam. And so therefore, the layout that you would need to make is constrained by the space available to you. So you would more often in 3D survey want to build something custom than you would in 2D. So on the Terrameter, the spreads are the files that describe the relative position of all of the electrodes. It tells the instrument how many cables are attached to it, tells the instrument which pins on the connectors are attached to which takeouts, and it then tells them where that takeout lies on the ground. As I said earlier, for a 2D survey, it would just give it an X value because you're only interested in distance along the line. For a 3D survey, you would have X and Y because you want to know how far along, how far across. And if you were doing borehole tomography, where you've dropped multi-core cables down water-filled boreholes, well, then you need an X location for the borehole and a Y location. So that's where the top of the borehole is. And then you need a Z value to say how far down that takeout is. So this is just an example from a 3D spread file where it's defining the position of all of the electrodes. So in red, that's just saying, hey, instrument, this is the first cable, cable number 1. And then it says, here's a description for an electrode. This is electrode number 1, that's its ID. It sits at X equals 0, Y equals 0, so at the origin of my grid of electrodes. And I'm going to name it electrode 1, 1. So that's what it will appear as on the instrument during the data collection when an electrode test is run. So it's saying this is cable 1, electrode 1. And then there's just a closing flag to say that's all of the description for this electrode. Then it would move on to the next electrode. So this one is ID number 2, and this one is positioned at X equals 1, Y equals 0. So one step into the grid along the first row. And this is cable number 1, electrode number 2. That's how I want it to be named. And then we have a closing tag for that. And then we can do that for every electrode along the cable. And then we would move on to the second cable and name all of those, and so on and so forth. The protocol is the kind of firing sequence, the order in which we would select electrodes to inject current in and select electrodes to measure voltage in. So very similar. These are all in what we call XML format. So it's basically a plain text, but you can group them if you have an XML viewer into tables. So it's much easier to handle the data, handle the information. So here we're saying this is a measurement sequence. And the first measurement we want you to take is to inject current between electrode ID 81 and 71. So that's coming from the spread file. And we want you to receive, i.e. measure voltage at electrode 1 and electrode 11, electrode 11 and electrode 21, 21 and 31, 51 and 61, and that'll be it for that measurement phase. Then the next one moves on, and that's a new current injection position and a new set of voltage values. So once we've defined where the current is going to be, we can put as long a list as we like of voltage measurements in here, and the instrument will then split that list up based on how many channels it has available to undertake the measurement. So what it will do is it'll look at that list and say, okay, I can do these ones in the first current injection, and then I'll do these ones. So I'll repeat the current injection, get the next set from that list, then the next set. And then once that list of receiver positions has been completed, it will move on to the next measurement sequence. So we have some protocol software online. It was made by a third party for their own use. They said we could take it and make it freely available. So that's on there. So you can have a look at generating your own spreads and protocols. Or alternatively, you can write them from scratch, just working in the XML format as we have here. So once we've defined our spreads, our protocols, we've worked out how we're going to lay everything out in the field, we've collected our data, then we're going to come home with a set of apparent resistivity values and other metadata surrounding that measurement. So what do we do with that workflow? Well, it's basically 7 steps. Step 1 is that we look at that raw data and we remove outliers, poor quality readings, and very weak responses. So we can look at the standard deviation on an individual measurement, and anything that has a high standard deviation, bin it. We can look at the voltage value that was measured, and anything that is particularly low that would fall into the noise floor, we can bin it. And then we can look at the actual apparent resistivity spread, and we can look for values that are particularly low, where there's a big jump down from the main bulk of measurements, or any that are particularly high and there's a big step up without anything in between, because apparent resistivity values don't change very rapidly from one cell to the next, one measurement position to the next. They should vary relatively smoothly. So we shouldn't see any big jump at the top or bottom of our spread of apparent resistivity values. So we can get rid of those straight away. Then we can do any corrections that are required. So that might be that we've shifted 1 or 2 electrodes in the field to be able to avoid a footpath or, an outcrop of rock or something like that. So we can double check that they are in now the correct position and not the regular grid as normal. And if there was any unintentional positioning of the electrode. So we maybe put the wrong spacing in when we set up the instrument. And instead of saying that it was a 5-meter electrode spacing, we accidentally put in 2. We could correct that at this stage. And then also apply any topographic correction. Was there a big change in elevation between electrodes? Do we want to add that in to make our inversion more accurate? Once we've done all that, well, then we can export, ready to invert. So whatever our preferred inversion package might be, export to a format that it can read in. And then normally your inversion package will also have some checks and balances that it will do to make sure that the data are good. So we can make a double check there that there aren't any remaining issues within our data set. Then we're going to run the inversion. And normally what I would recommend is just run it on the default values for the software that you're using, just so that you can get a sighter of what the model is starting to look like. So run that inversion, have a look at it, and then ask yourself 3 questions. Have you got a good fit? So that is the difference between the resistivity model it has presented you, the raw data that would have been collected from that, and the raw data that you have given it from the real world. If the fit is not good, i.e. there's a big discrepancy between the two, then it means your model is likely to be unreliable. If the fit is small, then it's an indicator that potentially your model is quite good. However, there are caveats on that. It needs to be realistic. So look at the data. Is this what I would expect from the geology that I'm working in or the type of target that I'm trying to record? So is it a realistic result? Because you can have a perfectly good fit on a totally unrealistic model. So is it realistic, and is it what I would expect? From that, I can start to make more educated choices in my inversion parameters. So that might be saying, well, it looks like the resistivity is changing quite rapidly. And I expect in this region that there might be a contact between, a very sharp contrast between low resistivity and high resistivity features. Let's say you were looking for a solution hole, something like that, a void. Then you would expect there to be a sharp resistivity contrast. So you could use what's called a blocky inversion, where you allow the model to have bigger steps between the resistivity values of one part of the model and a neighboring part. We might have other information that we can include in the model. So we might have data from other geophysical surveys that tell us where there is a particular layering. We might have some coring data that allows us to know at what depth there's a change in material. So we can put these parameters in to try and assist the model to get to a reasonable result. We then do the same review of that educated inversion. Have we got a good fit? Is this what we expect? Is it a realistic result? And if we're happy with it, well, then we can visualize the data or export it for use elsewhere for us to either report on or do something further with. So that's if we're doing our 3D survey. If we're doing 2.5D, where we've taken these 2D profiles and we are then creating a 3D volume to then run the inversion on, there is an extra stage, and it comes in at step 3. We would export the individual 2D profiles from our instrument or our companion software, and then we would need to combine them. So the example that I'm going to use is Res 2D / Res 3D. It's an industry standard. It's been around for a very long time. A lot of people know it. So it's an easy one to use as an example. So in Res 2D, there is the option to collate data into Res 3D Inv format. So when you buy a copy of Res 3D Inv, you get Res 2D Inv as well. And so you take your individual 2D files, you come in here and you use the option collate data into Res 3D Inv format. Now, one thing I would have to say is that today, the 25th of May, there will be a new version of Res 2D released, and the format will look very, very different from this. They've done a complete refresh at Sequent on how the software looks and operates. So if you start using it, I think it's today anyway, or tomorrow, the menu won't look like this, but I assume, I haven't seen it myself yet, that it'll be follow a similar format. So you collate data into Res3D-IM format, and it will ask you for a text file that describes the position of those individual 2D lines. So this is what the 2D file looks like, and you get a kind of example version of this file with the software. So all you need to come in and do is change it to match what you've done in the field. So the first thing you put in is you tell it how many files you've got, how many of these 2D profiles, and then you list each file and you give the parameters for it. So the location and file name of the first 2D file. You then provide the start position in Cartesian coordinates, so X and Y in your grid, your survey grid, and then tell the software whether this is an X line, i.e. running east-west, or a Y line running north-south. So you do that with a 0 or a 1 as shown in the file. And then you can tell it whether the line is running positive or negative. So this is basically flipping the profile. So if you had collected data in one direction and then moved across and then rolled back in the other direction, you can tell the software these lines are in opposite directions. So once you've done that for file 1, then you can move on to file 2. And what you can see here is this is a very small survey where there's just a ½ meter spacing between the profiles. So they start in the same X location, but they have a Y offset between each of the 2D profiles. So you select that text file. That then allows Res2D to go off, pick up those individual files, put them into the 3D block in their correct relative position, and then generate a 3D file. So right at the end of this file, you just put an entry in saying, I want the output file to be named this. And when you then come to process it, that will be the file that you'll use for the inversion. Okay, so with the last 5-10 minutes, I'm just going to quickly run through how this would look on an instrument. So for that, I will need to connect to my Terrameter LS, which is just over there behind me. So let's just make sure I'm connected to its Wi-Fi network. Yeah, so there it is. So my LS2 has a Wi-Fi network in it, and I am currently connected to that. I'm going to start what's called Type VNC. This is a free VNC viewing app that you can get these for PC, Android, Apple, Mac, Linux, everything. All computing can use VNC. So I'm just going to put in the IP address that's shown on the front panel of my instrument and say connect. And there we are, we're in. So this is the front screen of my Terrameter LS2. I'm going to tab along and create a new project. I'm going to create a new task, so that's effectively a measurement. I need to select the correct spread. Oh, that was lucky. It was the next one in the list. So this is a 3D spread with a 10x6 layout using our 4x21 cable set. So 4 cables, 21 takeouts on each, and they're being zigzagged in such a way that they produce a 10x6 layout. And then I'm going to undertake a gradient measurement with that layout. So electrode spacing, we can put in here whatever we would have in the field. So let's say we had an electrode spacing of 2.5 meters. And normally when you're doing a 3D, you would normally have equal spacing between the electrodes if it's true 3D, but you don't have to. Say okay. It'll then take me through to the settings page. And so what I could do is just load in, a set of settings for either doing res and IP or doing just pure resistivity. I'm not going to load in one of the preloaded settings, however, because I'm running this on a desk. So I want to make sure that I'm not going to blow anything up, so I'm just going to reduce the power right down on it. There we go. And I'm going to switch the electrode test off because I don't actually have any electrodes attached to the instrument. So I'll jump to the measurement screen and I'm going to create a new station. So this is telling the instrument whereabouts is that grid of electrodes. Am I starting at an origin or am I collecting at some other location within my survey area? And so we can roll the block around, so we can move it up, down, left, right, east, west, north, south. But I don't want to move it. I want to just start. So I say, okay. And then start measuring. It'll give me a warning. Make sure I'm not electrocuting myself. Just make sure that my resistor is plugged in. Yep. So I've just put a resistor across the end panel current outputs so that it thinks it's injecting current into the ground, but obviously it's just measuring random noise in terms of the voltage. So that's it. I mean, that's the 3D setup on the instrument and data collected. Really, with a 3D survey, the more difficult part of it is actually doing the layout in the field. Once you come to collect data, the creating a task, starting the measurement and reviewing the raw data as it comes in is actually the same as it would be for a 2D measurement. So it's giving me a measuring error because we're not attached to the ground. So it's just measuring noise. So it's telling me that these are very noisy readings. So I'll just tell it to ignore those for now so it can carry on running. So whether I'm doing 3D or 2D, this process is actually the same. I don't want to look at my pseudo section. That's not really of any interest to me. What's of interest to me is this standard deviation column. So what we're looking at here is a live table of results. Each one of these lines is an individual measurement channel within the instrument. So I've got up to 12 channels available on this machine. And then the bottom row is the transmitter details. So it's telling me at the moment that it has injected current on cable 1, electrode 9, and cable 1, electrode 19. It input 50 milliamps, that it was very stable. The standard deviation on the current is very low, and it used a particular voltage to push that current through the resistor that I currently have attached to the instrument. And again, the voltage hasn't had to change much because we're in a fairly stable environment. Then each of the rows is again telling me which electrodes are being used to take a voltage reading from, what voltage was measured during the cycle, the standard deviation, how much that voltage has changed, calculated resistance, which is injected current, measured voltage, an apparent resistivity, and then, because we're collecting IP, also a chargeability value. Again, we're not connected to the ground. This is just random noise, hence the slightly strange numbers that we're getting here. But this standard deviation column is the one that tells me whether I'm going to take good data home or not. If I'm getting values below 1% in that column, then I can be pretty certain that the data I'm collecting are sound. You know, if the measured voltage is stable, the current that's going in is stable, it's not being affected by external noise, we're not being impacted by poor contacts on the electrodes, and therefore we shouldn't have too many surprises when we get back to the office in terms of having lots of data that we need to remove. So that's the data collection. We can just quickly look at what we would do in terms of those processing steps that we talked about. We would, as the first steps, sort of steps 1 to, I think it was 1 to 3, which was filtering, corrections, and export, we can do in the LS Toolbox software. So if I was to create a project group, just call this webinar 3D ERT. Oops. I could connect to the instrument and download the data. As it is, to save a bit of time, I'll just add one that's already been downloaded. So, oh yeah, that was the right one. So this is what comes off the instrument. There's a project database which is the sort of average values for output current, voltage, measured voltage, resistance, apparent resistivity, temperature, battery status, and all of the kind of IP windows. So that's all contained in there. And then we also have raw data, which is full waveform. So that's showing us what the current has done, sort of 1,000 times a second it's being sampled, all the way through the current injection, so we can see what's going out, and also what happens on all of the measurement channels. Really good for assessing how much noise there might be in a data set. So I can open that up. I can look at the summary, which will tell me exactly what happened during the data collection process. It'll tell me where the data were collected, the settings that were used, and then the parameters of that particular file. And if I open the table up, this is everything. This is that database. So it tells me time, measurements, IDs, the measurement channel that was in use, the electrodes that were in use, what position they're in, which switches were being used. But the columns that I'm most interested in really are, let's have a look, these ones, input voltage, the variance, and the apparent resistivity. So if I was to sort my variance from large to small, I can get rid of anything that's over 1% and say, I don't trust that. I'm going to keep just the very cleanest data. I can then look at the input voltages, and I can look to remove anything that's less than, I don't know, 1.5 millivolts, somewhere around there. Depends on what the environmental noise is like on the site that you're on. But I can see here that I don't have anything anywhere close to that small. So smallest value is 140 millivolts. So I don't need to filter anything out there. And then I can have a quick look at the apparent resistivity values and see whether there's any unusual outliers. So I've got a negative value there. And then I've got a couple of very low values before we get into the kind of main spread that vary more evenly. So I can just say, okay, I don't trust those ones. I'll filter those out. Then have a look at the high end by sorting the table the other way. And it's a fairly even spread of values. So at that point, that's all I would do. Check the variance, check the signal strength, check the apparent resistivities. I would then right click and export, and then choose my Res 3D in format. As this is a true 3D dataset, it's already collated into that 3D file. If I was doing 2.5D, then I would process the individual profiles, export each of them as a Res 2D file, and then go into Res 2D as we looked at before, collate them, and then run the inversion. Okay, so there we go. That's a very whistle-stop tour of how we would undertake 3D survey. If you